Well, greetings out there in YouTube land. I was just in the process of biasing a brand new set of 4 6L6s in this AB764 twin reverb amp. And it occurred to me that I've been asked many times by viewers to prepare some sort of a video explaining how quad-ended amps are biased. So there's no time like the present. I haven't released a technical video in a long time, so let's do it. Okay, let's go ahead and discuss the theory and practice of biasing not only quad-ended amps but also double-ended amps so that we have it all very clear in our mind. If this sounds at all interesting, then please stay tuned because we're just about to get started. Let's talk for a few minutes here about how you bias amps that have 4 output tubes. This is something I've gotten comments and requests to discuss, and I guess this is the perfect time to do it. First, let's discuss what's involved in measuring output tube bias. It's based on plate dissipation in watts. In the tube manuals, there is a maximum value that you're permitted to approach but never exceed. Well, I'll show you in one of the tube handbooks where you find it. Okay, but to get this elusive figure, you have to do 2 other measurements and then multiply them together. One is the plate current in amps, not milliamps like you're used to hearing it, but in amps. So it's going to be a decimal number times the plate voltage. Now, on tubes that are grid biased, in other words, the cathodes are grounded, you can measure the plate voltage from the plate to ground. If the tubes are cathode biased, you have to measure the plate voltage from the plate to the cathode. Alright, now let's take a look at how we bias a normal double-ended push-pull amplifier. Although circuits may vary, this part of the circuit is almost always exactly the same. The B+, probably at the highest voltage level possible, and this is DC, okay, coming from the rectifier, is going to come up and go to the center tap of the primary of the output transformer. Now what we'll do to calculate our plate dissipation. Now I have those Eurotubes probes which does all this for me, but I'm going to do this manually because I don't think that most of you have those probes. Okay, so this is a method you can use to do your own biasing both for double-ended and quad-ended amplifier circuits. Number 1, we clip on our leads for our ohm meter and be sure the amp is off, unplugged, and the electrolytics are discharged before you do this. We'll clip on one lead to the lead of the B+ going to the center tap, and the other lead to the plate contact on the tube. And we're going to measure the resistance of this half winding of the output transformer primary. Once we have measured the resistance across this half winding, we'll take one of our probes away from the upper plate and clip it on down here to the lower plate and measure the resistance of this half winding. Now, since I say half winding, you're thinking that these 2 values will be the same, but they never are. No output transformer is wound exactly the same. Okay, so you've got to do both measurements. And I'll just do an example of one of them. Say I did that and I measured 250 ohms across this half winding. Next, you put your probes back as you had them for your resistance measurement, turn on the amp and let it heat up, and then measure using the voltmeter part of your digital multimeter to determine what the difference is between the voltage here and here. That's the voltage drop across this half winding. Let's say it's 7.5 volts. I put the little D down there for voltage drop. Okay, so we now know our resistance of our half winding, and we know the voltage drop across that resistance. We'll do the same thing down here. Okay, then look at our measurement is put into this formula where it is the voltage drop divided by the resistance of the half winding, and we'll get that answer in amps, okay, and it's 0.030 amps, or you can move the decimal 3 points to the right and change it to milli, which means 1,000th of an amp. Go 3 to the right and we have 30 milliamps. This is the way we normally talk about plate current, is in milliamps. But in our Ohm's law formula, it has to be expressed in amps. So now we have one of the two figures we need to calculate our plate dissipation, the plate current in amps. And in the case of the example, it is 0.030 amps. Now the next step is to figure out what is the plate voltage, and like I said, it depends on whether the cathode is grounded in the tubes in your circuit, or if it is cathode biased, which means there's a resistor between it and ground. If your cathode is grounded, then this is a grid biased amp, and what you can do is just hook your positive probe onto the plate pin of the tube and your negative probe onto the chassis somewhere, ground, and you'll get a measurement. If the tube is cathode biased and out of your cathode it has a resistor and probably a bypass cap between the cathode and ground, then you have to measure with the positive probe on the plate, the negative probe on the cathode. So you're getting the net plate voltage in the cathode biased type of circuit. So now we have both values that we need. We have our plate voltage, we have our plate current in amps, and now we will multiply. Let's use our example here, 0.030 amps for plate current, and let's pick a plate voltage of, say, 400 volts DC. Now, even though I've only shown the entire process for the upper plate, bear in mind we have to repeat every step of the process for the lower plate. We need to determine the plate dissipation for each of the output tube plates. Alright, so our 0.030 amps times 400 volts DC is going to give us 12 watts of plate dissipation. Now whether that's a good figure or not depends on the type of tube we're using and the type of circuit. That's really not what we're here to discuss, though. We're here to explain how we came up with this value. Okay, so now we've done it for our standard double-ended amp circuit. Now let me draw a quad-ended output circuit over here, and we'll see how it's really not all that much different than what we just did. First off, let's notice that instead of one tube here and one tube down here, obviously there's two instead of the one. Now, let's look at how those plates are wired. If it were a regular double-ended amp, wouldn't they B plus go up like we said and go to the plate? Well, the only difference is in the quad output amps is that the plates are wired in parallel, okay, on either side of the output transformer. You see how this B plus comes here and goes to the plate, and it also goes to this plate. That is parallel. If it went through this one and then up to this one, that would be in series, which would never work. Okay, so they're wired in parallel. So let's draw this so we have a very simple diagram, and then we'll work from that. Alright, let's take one last look at our double-ended diagram. A B plus comes to the center tap of the output transformer. One half winding goes to the tube plate here. The other half winding goes to this tube plate. Now let's look at our new diagram. Same output transformer, same B plus coming to the center tap, same half winding, but now it's feeding two plates in parallel, and the bottom one is feeding two plates in parallel. We use our ohm meter to measure the resistance between the center tap and this pin up here of either one of those plates, okay, so that we get the resistance here of the half winding, and we leave our negative ohm meter probe connected right here to where the B plus comes in. Take our positive probe from above, bring it down here and connect it to either one of these plates to get the resistance of the lower half winding. So far it is absolutely identical to what we did with the double-ended circuit. Next we turn on the amp, let it heat up, get it operating where it's stable, and we'll measure the voltage drop across that half winding. Now make a wild guess about the current that's going to be flowing through this half winding. Isn't it going to be double here than it was here? There's two plates. Okay, so wouldn't you expect the V drop to be probably about double, because it's directly related to the plate current, to be about double what you saw over here with your double-ended amp? Okay, so let's make up a figure that is double what we had. We had 7.5 volts. I think it would be reasonable to expect a 15 volt voltage drop, because we got 7.5 being dropped by this plate, 7.5 being dropped by this plate. So let's write that down. And let's say that half winding resistance was the same as with the double-ended amp. So it's the same, it's 250 ohms, but now the voltage drop is going to be twice as high. It's now 15, because there are two plates instead of one. When you divide 0.060 amps, or 60 milliamps. Now some people get to this point and get all panicky because they'll say, oh my God, 60 milliamps, oh my tubes are going to red plate. Well, there's two of them. That's the average of the two. So let's divide this figure by 2, and we see that the result is just the same. The tubes are operating at the same plate dissipation in the double-ended amp as they are in the quad-ended amp. They're both, in both cases, they're operating at 30 milliamps of plate current each. Now it should be remembered that this is an average of the two tubes. One could be 29 and the other could be 31. One could be 25 and the other 35, which would probably be acceptable, okay? But what if one is 10 and the other is 50? That's not a good setup, okay? So you have to beware of the fact that you are using an average plate current for these two. Then we'll measure the plate voltage of the tubes in exactly the same manner that we did for the double-ended amp. Okay, positive probe on the plate, negative on ground if it's grid biased, or on the cathode if it's cathode biased. And it's not a bad idea to check them both. Okay, check them both. And do the same down here. Then once you get that plate voltage, and let's say it's the same as it was for our double-ended example, it's 400 volts DC, and we multiply, and we see that each of our 4 tubes is operating at a plate dissipation of about 12 watts. We know that 12 watts is the average up here, and say if we got the same values for the lower pair, that 12 watts would be approximately correct for each of the lower pair. Now, one tip-off that the tubes are grossly mismatched, like I said, 10 and 50, is that if you see quite a disparity between your plate voltage when you measure each of the plate voltages, the plate voltage will be lower in the tube with the highest plate current. So if you do have a 10-50 relationship here, your plate voltage will be much higher on the 10 and much lower on the 50. If, however, your plate voltages come out about the same, or identical, which is really generally the case, then you know that these tubes are fairly closely matched. So in conclusion, the two methods are virtually identical, except for the fact that you are dividing by 2 to get the average of the two tubes in the upper end of the output transformer winding, and you're dividing these by 2 to get the average plate current in the lower. Okay, that's one thing to remember. Divide by 2. Next thing is you're getting an average. Those are not absolute values for either. It's only the average of the two. Okay, and the plate dissipation that you see in your tube manual, and I'll show you in just a second, is correct whether your amp is double-ended or quad-ended. These tubes should operate under the parameters described in the tube manual, whether there's 4 of them or there's 2 of them. Alright, I'm looking here at my Sylvania electronic tube handbook. If you don't have one of these, or by RCA or other companies, they're on eBay and you can get them relatively inexpensively. I turned it to the 6v6 page. The section that you want is maximum ratings. Okay, there's all kinds of other stuff here that can be very confusing, but maximum ratings is what you want, because we want to know what is the maximum plate dissipation. See it right there. For a 6v6 is 12 watts. Okay, so let's write that down and talk about it for just a second or two, and then just have a couple final statements. So let's look at the 6v6 tube. We said the maximum plate dissipation from our book was 12 watts. Now, if the tube is cathode biased, how do you know that? Well, look at either the tube in the circuit or on the schematic. Look at the cathode of the output tube of the 6v6. Does it have a resistor and parallel capacitor to ground? If so, it's cathode biased. This resistor is what applies the bias to the tube, okay, and it's connected to the cathode, there, hence the name cathode biased. If, however, the cathode is just grounded, there's no way that's going to bias the tube. We have to go in and grid bias it, okay, and that's in another video and another day. But for now, if your output tube is cathode biased, I feel comfortable at 80 to 90% of maximum. I know that for a long time people have been saying you can go 100% or maybe even a little over if you're cathode biased. Well, it's a waste of time, it won't sound any better, and your tubes won't last as long. 80 to 90%, which would be what, about 9.6 to around 10.8 watts, is great for cathode biased amps. Grid biased, you really have to go down. Classically, they've always said like 70%, okay, which would be 8.4 watts. But through my own observations and experimentation and reading on the topic, I can tell you that that's way too high. Around 50 to 60%, which would be what, 6 to 7.2 watts, is probably ideal for grid biased output tubes. Here's why. The plate current in a cathode biased tube does not really rise and fall very much depending on how the tube is driven. So while you're playing, you're strumming away, you're up at a high volume, and you're just having, you know, your greatest night ever. Well, the excursion of the plate current is not that great. It's going to hover right around the value that we found for it, around 30 milliamps, in a cathode biased tube. In a grid biased tube, that's not the case. This sort of corrects for, as it starts to elevate, it self-corrects. As it starts to come down, it self-corrects. There is no self-correction here. If you started off at 30 milliamps at idle and you're playing at like a really high volume and you're really hitting the strings, your plate current can go up to double or maybe triple this value. It goes up a lot higher than many people realize. So you're better off starting at a lower idle current, okay? And so when you grid bias, I would go to like 6 or 7.2 watts of plate dissipation. From my experience, it sounds just as good as the 70 or 75%. The tubes run cooler and they'll last a whole lot longer. So there you have it. Okay, I think you're going to find that more and more people are shifting to this lower value. A couple final statements here just for safety. When you're doing the resistance measurement of the half windings, the amp is off, it's unplugged, and all of the filter caps are drained. Okay, using a tool that I've shown you in some previous videos, you drain all of those electrolytic capacitors, every one that you can find in the circuit. That's when you're measuring resistance. Now, when you're measuring the voltage drop, the amp's on and operating. So you can't really, try to drain the electrolytics. They're upcharged and this thing is running and you've got 400 volts here on the plate. Be very careful. Keep one hand in your pocket. Here's why. If there's 400 volts on this plate and I touch it with my finger, and then on my right hand I touch the chassis, the 400 volts will take a shortcut right through me to the chassis, and the results, it could be fatal. So when you are messing around with a live amp, you keep one hand in your pocket so that you cannot possibly complete a circuit between, say, the plate voltage and the chassis. Now I can tell you from experience, every once in a while you might brush something or touch something that's connected to the plate and then touch the chassis with, say, this part of your finger, so that 400 volts goes through this part of your finger, and it is not something you will want to have happen more than once. It hurts like the devil. Now if it goes all the way through you, from arm to arm, it will go through your heart, and just like those paddles can restart your heart that you see on the ER and the other TV shows, well, they can have the opposite effect too. It can stop your heart. So don't do it, okay? You don't need your widow to find you out in your amp room laying on the floor stiff as a board because you didn't keep one hand in your pocket. Well, I guess that about does it on today's technical video covering the topic of biasing quad-ended amplifiers. I hope you enjoyed it. I want to take a few moments to thank all my Patreon patrons and PayPal contributors for keeping us on the air, advertising free for another month. Should you choose to join them in supporting our channel, I will put links in the video description to assist you to do so. Also, please be sure that you are subscribed. Many people think they're subscribed, and when they double check, they aren't. We're trying to boost our subscription numbers right now, and we really appreciate your help in doing so. Also, if you'd like to see a practical demonstration of the theories and practices that we've discussed in this technical video, I will be posting the video covering this twin reverb amp in about 10 days to 2 weeks. So and when I do, I will put a link in this technical video's description so that you can connect to the twin reverb video and watch the processes that we've discussed today. And meanwhile, I hope you stay healthy, happy, and by all means, stay tuned. We'll see you again in about 10 days. Bye for now.